So welcome back, everyone. We're going to listen to Michael Walter from Bochum, and he's going to talk about tensor symmetries and optimization. Michael, the stage is yours.
Thanks so much. Is the audio okay? Do you hear me all right?
Yeah.
Camera is wildly following you, but doesn't quite work out. Super. Yeah. Thanks a lot for having me. I'm very sorry that I couldn't be there in person. I see all the fantastic, friendly colleagues in the audience. Yeah, sorry to make you suffer through another Zoom talk, which will probably not as nice as Norbert's. So I want to talk about tensors, of course, as everyone does here, and symmetries, as many people do here also, and how it ties in with optimization. And in some sense, the motivation for my question, well, I guess there's two motivations for the talk. I mean, one is I'm going to try to some extent to set the stage for David's talk. And what David will do is he's going to basically come back to the question that Norbert discussed in part of his talk, right? So he discussed this fundamental theorem, and really what that is trying to answer is the question: when are two tensors equivalent in the sense of generating the same tensor network states, right? And there's this obvious symmetry. Is there more? What does that symmetry mean, and so on? Okay, so it's really the talks about equivalence of mathematical objects, symmetries, how to reason about them mathematically, and how to also algorithmically try to decide problems about those. Okay, so that's sort of my the segue maybe into this talk. So group actions, right? We use them as a way of modeling symmetries and notions of equivalence. Here's a discrete example that we all know, right? Graph isomorphism, that we're commuting labels of vertices. Two graphs are isomorphic, we can commute one vertex set onto the other, such that the adjacency matches. And in that's of course a super general question. There's a super general setting, and there's sort of a very general meta question that we can ask. I mean, if we are sort of maybe wearing our structural hat, right, we could ask, how can we mathematically describe when two objects are equivalent? If we were more of in a computational hat, then maybe we want to know rather, how can we actually effectively or algorithmically decide that? Okay. And I mean, that's of course a very rich source of problems, right? Graph ISO famously, we don't yet know polytope algorithms, but we know lots of smart algorithms. Seems to be on a good path, perhaps, to finding those. We know that for matrices, right, they're under left and right multiplication. Two matrices are equivalent if they have the same rank, but then for tensors, of course, many people discussed, things are more complicated, right? A tensor rank is a difficult thing to compute, unlike the matrix rank. Also, tensor rank does not capture equivalence, right? So that's sort of a difficult and rich and interesting sort of source of problems. Other examples are, being able to, so it's a very fundamental problem given black box access to a polynomial, testing whether that polynomial is zero or non-zero, easy to do randomly. And right, you just pick a point, you evaluate the polynomial. We don't know how to do that efficiently in general, deterministically efficiently in general. But that's really an equivalence form, right? So the question is a polynomial equivalent to the zero polynomial. There's a black box evaluating polynomial equivalent to zero polynomial. And then maybe more from a structural perspective, right? This is about computing normals forms, describing moduli spaces, describing reasoning about invariance from a perspective of mathematics. So I want to sort of focus on tensors, right? And sort of study their symmetries, as many of you have done and spoken about these weeks. And the right notion of symmetry, of course, depends very much on the application that we have in mind, right? And as with so many talks. So for example, if I have a two tensor matrix, I mean, there's already perhaps two choices, right? I could study matrices with respect to row and column operations that are separate, like on my previous slide, or I could act by conjugation, right? So base change, the same base change on the left and on the right. So here I wrote down conjugation just for change's sake. I guess in Norbert's talk, he discussed matrix product states as an example of tensor networks. So matrix product states were these one-dimensional things that look like so. So you start with a three-leg tensor. You control these horizontal dimensions are the same. You put them, for example, on this pair on a circle. You connect these horizontal legs along the circle. If you put the same tensor everywhere, that's called a uniform or translation variant matrix product state. And as Norbert explained, there's a natural symmetry here, right? On each of these edges, you can insert G inverse, which is the same as for each tensor, which is the same tensor everywhere. You insert a G on the left and a G inverse on the right. Okay. I know such a three tensor is a matrix tuple, right? It's labeled by this index that I guess I call J on the left, which is the index sticking out to the bottom. So really the action, the symmetry, natural symmetry for that problem that Norbert discussed is what you could call simultaneous conjugation. The simultaneous conjugation action of, say, GLN or SLN on matrix tuples. Okay, matrix tuples, aka 3 tensors, where we think of this last index simply as labeling the tuple, but it's not important for the action. So these are natural symmetries, right? You could ask, are they these all there is? That was the discussion of the last talk, and will also be discussion of the next talk. Here's another example. It's again about matrix tuples, but we can also use matrix tuples for different purposes. We can use a matrix tuple, again, MJ, to define what's called a completely positive map, right? So a complete positive map is a linear map of this form, sends PSD operators to PSD operators, even when you tensor with the identity. Here there's also a natural action, and the thing is that here these MJs, it's sort of very natural to allow yourself to multiply them from the left and from the right by different matrices, different invariant matrices. Okay, because this thing is completely positive regardless on, say, any positivity properties on M, so there's no reason to restrict them to be the same from the left and the right. So what you get here is the so-called left-right action on matrix tuple. So given 2 invariant matrices G and H and a matrix tuple MJ, you left multiply by G and you right multiply, say, by H transpose or by, say, or by H inverse, whatever you like to turn this into a right action, into a left action. Okay, so these are 2 different actions, right, for the same vector space, different group, 2 different symmetries, matrix tuples / 3 tensors. And then, of course, another thing that again, many of you study and are interested in is I guess what we call the tensor action. So here for 3 tensors, if you have a 3 tensor, then maybe this 3 tensor corresponds to a quantum state of 3 parties or particles or systems, or to a bilinear computational problem, if you're wearing the algebraic complexity hat. Then a natural symmetry here that you might want to consider is your arbitrary local base change. Okay, so you have a triple of invariant matrices, you have by A tensor B tensor C. Okay. So just to compare these 2, right, what the action here, if you think about it as a 3 tensor, it's more like A tensor B tensor identity, or I guess I called it G and H, G tensor H tensor identity. So here we're acting everything, we're treating all the 3 parties in the same way, but we don't allow commuting the tensor factor. So these parties have their own identity. Okay, so these are symmetries, and we want to sort of come to terms with them. Okay, and for example, one question you might want to ask is, when are 2 tensors equivalent under such an action, under such a symmetry? Okay, so how to decide equivalence? And I guess there's many approaches, right? Maybe there's a and one possible approach would be to sort of single out. So the group action, right? It defines the equivalence class, defines an orbit, and what you could try to do is in each orbit, in each equivalence class, pick out a normal form, a canonical form. Okay, some kind of representative that is somewhat natural. So don't want to make too many arbitrary choices. And you kind of want, that it's sort of pretty unique, maybe as unique as can be. So you want that this normal form satisfies something like what Norbert called the fundamental theorem. So kind of equivalence should kind of boil down to having a common normal form apart maybe from symmetries you can get rid of, such as this, unitary symmetries typically in the game. So we'll make this more precise in a moment. Okay. Or maybe sometimes you can even nail this down more by making more choices. Okay. So, by the way, you should interrupt me anytime. I'm not sure if it's easy for you to do just by talking or whether you have to press some button, but don't have to get through all the slides.
We will interrupt you if we need.
We will stop.
Fantastic. Super. Yeah, here's an example. Okay, conjugation matrices. So G acts on a matrix M by G inverse. Right, we can define normal form by just saying, okay, let's diagonalize the matrix. Fantastic. And then the diagonalization or the eigenvalues with the algebraic multiplicity would be the normal form. Okay. So that's great, but of course we can only diagonalize generic matrices, not arbitrary ones. For general matrices, so we can do generic but not general. For general matrices, we have the Jordan normal form, right, that we have to worry about. So here's sort of an example. There's a 2x2 Jordan block with a little 1 sitting at the top. For some reason, I picked a different eigenvalue sitting, starting the next block and so on. So that's a bit annoying, right? So the prescription maybe doesn't exactly work. Diagonalize your matrix, and that's the normal form. But one here is an idea. Okay, in the Jordan normal form, of course, whether I put a 1 here or any other number, that's pretty arbitrary. I can always apply a similarity transformation that turns the 1 in the Jordan normal form, so the 1s, if there's many, into some arbitrary number. For example, a very small number, epsilon. Okay, and then I could allow myself to let this epsilon go to 0. Okay, and that's of course related to the fact that the Jordan normal form is unstable in a way, right? It's hard, it's tricky to compute, because if you perturb your matrix slightly, it becomes generic. And similarly, because it's epsilon, is arbitrary, in the drawn normal form of the same matrix, but you can make it as small as you want, or let it go to 0. So if you allow yourself that freedom, if you say, okay, I'm happy with taking limits, but with taking limits, then of course any matrix can in some sense be asymptotically diagonalized. So in the sense that you can take limits of conjugation orbits such that it becomes diagonalizable. And it's also easy to check asymptotic equivalency, right? It's because you're basically just killing off the drawn block structure. So the only thing that remains is indeed the eigenvalues with the algebraic multiplicity or the characteristic polynomial, if you want. So that's maybe interesting, right? So sort of by making the problem a little bit more robust or fuzzy, or allowing yourself to take limits, somehow this question can simplify. Here's okay, but of course one question remains. I mean, here I guess the idea of diagonalizing fell from the sky. Is there sort of a general principle by which we can find suggestions for normal forms? Here's sort of another example that I guess many of you know. So I'll be quick. So suppose X is a matrix with non-negative entries. Okay, and I want to study some kind of symmetry of this class of matrices. Okay, and single out a normal form, but I want to keep the matrix to have non-negative entries. Okay, so it's not sort of a good, and I want the symmetry to be a group, right? So it's not good to apply inverted matrices indefinitely, right? Because you'll introduce negative entries. But one thing you can do is you can basically just multiply the rows and the columns by positive numbers. That will certainly preserve the structural feature that the matrix is non-negative entries. Okay, that's also going to preserve the support, for example, which you might like. For example, if you think of X as a joint probability distribution, you will not change its support. Okay. So that's what we call a scaling of a matrix, a left and right multiplied by positive diagonal matrix, or rescaling rows and columns by these numbers AI and BJ. So now let's also again, randomly pick what we could call a normal form, some kind of nice criterion that's not generic, always satisfied, and that seems to pretty uniquely nail down maybe a matrix in that equivalence class. And we'll pick the notion of doubly stochasticity. Okay, so we'll say, let's say a normal form of X is a scaling such that the row and column sums are both 1. Okay, so that scaling that is a doubly stochastic matrix. Okay, scaling is again my name for a matrix obtained by applying this group action. And the matrix scaling problem asks, okay, given a matrix, compute this thing, and again we allow ourselves limits. Okay, if you don't allow yourself limits, then it's again maybe an numerically unhappy problem, but we allow ourselves to take limits. So we're looking for approximately doubly stochastic scaling, so scalings where the row and column sums are as close to 1 as we like. And it turns out there's a beautiful algorithm for doing so due to Synchron. Again, many you'll know it. And basically the idea is it's easy to make the row sums exactly equal to 1 by messing with a column sum. So what you do is you have your matrix here, you divide each row by its sum. Okay, so here it gets 1/3, 2/3. This guy just becomes 1, 0. Now you normalize the columns, you divide each column by its sum. Okay, so you get 1/4, 3/4. Or 1/4, 3/4, but this guy gets just plain normalized to 1, 0, and so on. You repeat this procedure. This matrix converges, okay, and it converges, say, after, I guess, an even number of iterations. It's going to look like a really small number, 1, 1, 0. Okay, well, this number close, a really small number close to 1, 1, 0. Clearly, as epsilon goes to 0, that converges to sort of like an anti-diagonal matrix. So that is a swap matrix, which is doubly stochastic. Okay. So that's cool, and one can show, and has been shown that this actually works whenever possible. It works in polynomial time the size of the matrix. It's very cool. There's lots of so what's the point, right? It's this, I mean, from the perspective of, I guess, the motivation, right? It basically allows you to compute these normal forms efficiently in a way, okay, or to any desired approximation. So that's very nice. Okay, and there's a unique such doubly stochastic scaling that you can get by limits from a starting matrix X. Okay, so we sort of solve the problem for our somewhat perhaps arbitrary definition of what, I mean, it's not clear why we picked doubly stochastic, but if we do so, apparently we get a good theory. Okay, there's other characterizations. I mean, well, you could ask, when is it even possible to solve that problem up to arbitrary precision? That's possible when a permanent of matrix positive, or if you think of the support of the matrix as defining a bipartite graph, then it says that this support, so the support matrix, so this bipartite graph admits a perfect matching. Okay, so here, for example, perfect matching, right? So there were 2 vertices on the left because there's 2 rows, 2 vertices on the right, 2 rows. The connectivity was like a cross. Okay, so that's a bipartite perfect matching in the support of the original matrix. Okay, so this problem has lots of applications that maybe I don't want to go into, but rather I want to ask, why is it that this nice algorithm worked? Is there sort of a more general perspective? Is there like a way, like a more general setting in which we can find a very general proposal for special normal forms, sort of without thinking, and then maybe we have to think in order to find a good algorithm, and we are still thinking about that in general, but at least there's sort of a natural proposal. Okay, and so with that being motivated, I want to sort of introduce the general setting of the talk. Okay, and we'll come back to interesting tensor examples in a little bit. So setting will be, we have some nice group, a reductive, complex reductive algebraic group. So you can think of that as a subgroup of GLN, let's say closed under daggers and it's cut out by polynomials. Could be GLN, SLN, product of that. Tn I'll write for torus, so a diagonal, complex diagonal, and n by n matrices, so n non-zero diagonal entries. This group will let act on a vector space of some other dimension m by linear transformations. And this data then determines all that we want to play with. Okay, it determines orbits. So given a vector v, the orbit I'll denote by gv. So everything I can get by applying this group operation. And we also get closures. Okay, and here's sort of the simplest non-trivial example. If your group is simply a single non-zero matrix, a single non-zero complex number in C star, right? So C stars are non-zero complex numbers. You have such a number G. You act in a 2D vector space, and here, okay, the idea is multiply the first coordinate by G, the second one by G inverse. And then sort of generically, right, orbits look like so. Why do they look like that? Because there's an invariant, which is x times y equals constant, right? So the product of the two coordinates is constant, clearly. And so that describes these blue curves generically. But there's sort of more special points, right? For example, the origin, okay, that is just its own thing, right? Its own orbit, because this is the left-hand side is, I mean, for each G, that's a linear map, right? So it sends clearly 0 to 0. And there's also other orbits, right? Like these green ones, where if you start at a point 1, 0, the orbit is going to be any point with a non-zero first coordinate and a 0 second coordinate. So in particular, well, it's intersection with a real plane. R2 looks like so, right? So there's this sort of line with the 0 point taken out. Okay, so this green orbit, it contains 0 in its closure, whereas these generic blue orbits, they stay far away. Okay, they stay, well, not far, but they stay a bounded amount of they have bounded distance. Okay, each of them their own bound. Okay, so that's sort of these two different kinds of orbits. Okay, and of course there's also say this vertical line without the origin. And it's sort of interesting that the green line and the green line without the origin and the vertical line, so horizontal line without the origin, vertical line without the origin, their closures meet, right? Their closures meet in the origin. Okay. Whereas, for example, these blue orbits, they actually close. So why do we actually have to even worry about closures, right? That's because our symmetry groups that we are studying here and that I gave in the examples before, they're not compact, right? So closures in general make a difference. Okay, so given this data, now we can sort of ask, an abstract version of the question we asked before. So we could ask, given two vectors in this representation space, so let's call them V and W, are they what you might call asymptotically equivalent or approximately equivalent to any arbitrary position in the following? And here's what I mean by that mathematically. Is it the case that there exists a point that is both in the closure of one vector V and is also in the closure of the other vector W? Okay, so it's a bit like with these matrices. If I have two matrices with some arbitrary Jordan block structure, then the diagonal matrix that has the same eigenvalues but no Jordan blocks, so, or one by one Jordan blocks if you like, it's in the closure of both of them. Okay, but neither of the two starting matrices are in each other's closure. Okay. So that defines a natural equivalence relation. It's basically the robust version, the version that you get by checking out two things in the same orbit, but you allow yourself to take limits, okay? But you want to get out an equivalence relation, so that's that one. And it's very natural, right? For example, for tensor networks, right, the tensor network state that is defined by a tensor, that's of course a continuous function of the tensor. So we're completely happy with taking limits. There's no reason not to allow yourself to take limits when you define normal forms. We're happy to throw away stuff, okay? Just like, like little off-diagonal blocks in a Jordan block. And that's indeed actually what happens when one reasons about these fundamental theorems, and I'm sure David will come back to that later. Okay, so given that definition, so that's the definition, right? So that's asking a problem. We could ask, what's the right normal form to answer such a question? Okay. So we'll come back to that in a moment. And it actually turns out that even a very special case of that, or a seeming special case of that problem is already very interesting. It actually helps answer that second question. And it's basically just trying to come to terms with this problem when one of the vectors is 0. So basically what you could ask is, given a single vector V is 0 in its orbit closure or not, right? So it's really asking, are you a blue orbit, which does not have 0 in the closure, or are you a green orbit? So you do have 0 in its closure. So it's really sort of the baby case of that first problem, but it actually also relates in a deep way to the second one. And I want to explain this next. Okay. So let's start with that, seemingly very special problem. So the question is 0 in the closure of an orbit. Okay, so on the right-hand side is a picture where it would not be. So there's many ways of interpreting that question. Okay, so one algebraic way of interpreting that question is as follows. You could say, well, if you have an invariant polynomial, right, then, well, it's a continuous function, it's invariant under the group action, so clearly P of E equals P of 0 for any invariant polynomial. And it turns out that for these nice groups and group actions that we consider, that's also sufficient. So you could try to attack that problem by using algebra, by using invariant theory. And if you replace, this point 0 by another point W, you actually exactly characterize this notion of equivalence that we defined on the previous slide. Okay. So that's one approach. Another approach is to say, so really what's going on here is we are trying to solve an optimization problem. We are trying to minimize the norm of all vectors in an orbit. And if, well, we can minimize that norm all the way to 0, like maybe in the limit, then the answer is yes, and otherwise it's no. So we can think of this as an optimization problem, right? That the following: minimize or infimize, if you like, norm of G dot V over the group. Okay, or you could say properly you're minimizing over vectors in the orbit closure. So that's the thing you can do, right? It's natural, pretty natural. There's not so much data you have to pick. You basically have to pick a norm. And usually then you also pick a compact subgroup of your group that acts here. For example, a group of unitaries that leave that norm invariant. That's sort of the standard setting that you would take. But it's fairly natural, right? There's not so many choices, in particular, there's few problem-specific choices you're making here. So what's interesting is that actually the minimizers to this problem, they provide a natural candidate for normal form. Yes. So right, because I mean, you're cutting down the space, the third space enormously, right? And generally, you start out with this orbit by this maximally compact. But you start out with an orbit or an orbit closure for a non-compact group G, and now you're minimizing the norm, and it's clear that there may be many minimizers, right? For example, if you have a minimizer and you apply something that acts unitarily, it's again going to give you a minimizer. But you cannot apply an arbitrary group element, right? So it cuts down the search space or the space of candidates enormously. And you could say maybe that's a good choice for a canonical form. Okay. In this conjugation example, like I gave before, it's a bit like looking at the set of all normal matrices in the orbit. Okay. And then if you like, you can pick out, your favorite thing, for example, by picking a basis, which is what we did for conjugation when we said, I want a diagonal matrix, right? It's not clear what diagonal means a priori in the setting. But once you pick a basis, you can even cut down things further. Okay. So the idea is let's take minimizer. So more precisely, not minimize in the sense of elements of the group, but rather vectors in the orbit closure that achieve a minimum norm in the orbit closure. Let's take those as candidates for normal or canonical forms. And then it is a fact, like I was saying, that they satisfy a version of a very general fundamental theorem, namely those minimizers, they're unique up to unitaries, or more precisely, again, there's a compact, maximally compact subgroup of this general reductive group G that we assume acts unitarily with respect to this norm, and that's the amount of freedom. So, for example, if you act for any of the actions we had before, it's the uniqueness is up to the corresponding unitary groups, UN or UN times UN, and so on and so forth. Cool. Okay, so that's one thing. The other sort of part of the message is suppose now you're trying to do this algorithmically, okay, and so that's one thing. Okay. So what you could do is, well, clearly, sort of, if you have a minimization problem and you don't know how to solve it, you're going to take a derivative and set that derivative to 0. Okay, so that's what we have here. So you could say, okay, let's try to find a group element such that the gradient at that new point, G dot V, is close to 0, right? So that's clearly going to be true if G dot V is an approximate minimizer. It's not so clear if the converse holds, okay? So it turns out that this problem here actually is of significant interest in many applications. And if you apply this whole machinery to this matrix scaling setting that I showed you earlier, then you'll find that this condition exactly demands that you're looking for an object that has doubly stochastic rows and columns. Okay, because it turns out that this gradient will compute something like the traceless part of the row and column sums. So it turns out that's actually a very interesting object. Often it's very interpretable. Okay. So that's nice. Okay, and what's even nicer is that actually that's an equivalence. So solving that scaling problem, minimizing the gradient, turns out to be equivalent to minimizing the norm itself, because this norm function is geodesically convex or even log convex. Okay, and then it turns out there's also beautiful polytopes, and hopefully we'll see some of those, because I think they relate to polytopes that some of you like and have studied and used to define cool measures for tensors, like versions of tensor rank and so on. So I want to come to that in a little bit. But that's sort of the big picture. So I want to discuss two things in the following. I want to give you more examples, okay, a few examples, including some that connect to tensors. Then I want to sort of, tell you how one can attack now this problem. Okay, how can one attack this problem algorithmically by relying on this connection between algebra and convexity? Okay, so under optimization. Let's look at 2 examples. So one is this matrix scaling case been before, and one thing you may already be worried about is that in this matrix scaling business, I looked at entry-wise positive matrices, but my general setup was a complex algebraic setting. Okay, so where does the positivity come from? So let's set up things like before, but let's do everything complex. So G is a pairs of diagonal complex invertible matrices. Okay, so these G's and the H's, they're just complex numbers, non-zero complex numbers. M is going to be now a complex n-by-n matrix. So that's the group action that we study. Now I want to minimize the norm of a given matrix, L2 norm. It's pretty canonical, pretty nice. With respect to that group. Okay, so I'm interested in minimizing the norm, L2 norm. The sum of squares, so I guess I do norm square here. So it's the sum of squares of the entries after rescaling. Okay. So clearly the ij entry of that matrix is gi times mij times hj. So I'm computing absolute value square and summing over I and j. Okay, I'm infimizing. So now clearly that's an absolute value. It only depends. It doesn't depend on the full strength of the complex number, but only on its absolute on its magnitude. So I can restrict to positive numbers, gi and hj. Okay, so there's some positivity coming in. And I'll call these, well, or rather they're squares, I'll call e to the xi and e to the yj. Okay. So if I do this, I'm going to infimize over real vectors now, x and y, which are these exponents. Okay, so the gi absolute value squared is going to be e to the xi, and likewise for yj and hj. So now this is the norm minimization that I'm interested in. And it turns out that is right. It's like a sum of exponentials with positive coefficients. That's it's called a polynomial, and this general optimization problem is called a geometric program without constraints in this case, right? Because you're minimizing over all arbitrary vectors x and y. Okay. And such things, they are in great generality, they're log convex functions of x and y. Okay, so that's very cool because it means here very concretely we see now that minimizing that function is equivalent to setting its gradient to 0. Okay, so what is the gradient of that function? Okay, it turns out that if you compute that gradient, right? Then, well, if you suppose you take the xi derivative here, right, then, well, you're singling out one I term in this whole sum, but you're still summing over j. Okay, so what you're doing is you're going to compute the ith row sum of that matrix. And likewise, if you compute the yj partial derivatives, you're going to compute the column sums. So the gradient at x equals y equals 0 is exactly a vector of length 2n, right? Because it's the function is defined on R to the 2n. The first component is the vector of row sums, second component is the vector of column sums. Of which matrix? Well, not of the original matrix, but of the matrix with that is entry-wise non-negative, and its entries are absolute value of mij squared. Okay, so that's how positivity enters sort of again. Okay, I was hoping that someone would complain and say, well, clearly this infimum is 0 because I'm optimizing and I can just let all these g's and these h's to be epsilon, and then let epsilon go to 0. So what are we doing here? And indeed, we don't want to set the row and column sums to 0, right? We want to set them to the identity because we want a doubly stochastic matrix to, out of this game. So the trick is the following: you replace the group by the group that I call STN, which is diagonal matrix with determinant 1. If you write them as exponentials, this means that these exponent vectors, their coordinates should sum to 0. And now the gradient is the projection on this vector of row and column sums onto pairs of vectors. Each of them has n coordinates, but they should be traceless. Okay, so projection on the traceless part in each component. And okay, how do you project and trace this part? You subtract the suitable multiple of the identity. And so now we are in business, right? Because now we see that minimizing the norm or norm square with respect to this subgroup is exactly the same by convexity as setting the gradient to 0 and setting the gradient to 0 and making it such that the row and the column sums, they are multiple of the identity. Okay, and then of course you can make that an arbitrary multiple by multiplying with some scalar. Okay, so what we see is that norm minimization and this matrix theorem problem it's equivalent. Actually, the proposal for this normal form, so why did I pick up this stochastic matrices? It arose naturally from the general principle. Whatever you do, you simply try to minimize norm with respect to your natural symmetry, and you see what comes out. Okay. And this convexity also sort of explains why these greedy algorithms work, because you're sort of you're doing local minimizations, but because it's a convex function, local minimization is the same as global minimization. And once you see that this is all you're optimizing over, you can also try to design more cutting edge algorithms, and people have done that. Okay, so just maybe as one comment, this is a particular action of a commutative group, or what people call algebraic tori. If you look at general torus actions on general fundamental representations, you get exactly something that's a problem that's at least as hard as linear programming, and it captures what it exactly captures is all these unconstrained geometric programs with arbitrary coefficients and arbitrary exponents, linear functions in the exponent. So sort of, I guess, again, there's some richness in the setting, right? I mean, it captures, these 1.5, very popular optimization paradigms. All right. So that's one thing. Okay, fantastic. I think the next thing that would be logical to talk about is this would be to try to look at sort of non-commutative generalization. I mean, now we want to see what happens with non-commutative groups, what happens with tensors. And I guess I gave you 2 tensor examples before, or 3. I mean, generally tensor examples with more than 2x. One was matrix tuples, and the other was 3 tensors. Okay. And I think maybe I'll just only very briefly comment on the matrix tuple case. I mentioned to you, right, that any matrix tuple defines a completely positive map. I think my notation changed a little bit. So now these operators defining the map are called xk. Okay, so xk is the matrix tuple, k being the index into the tuple. So this thing, again, is called a completely positive map. Again, the way we act on it, so we say a scaling of such a completely positive map, we simply do by left multiplying all the xk's by the same matrix G, same invertible matrix G, and right multiplying it by H transpose from another arbitrary invertible matrix H. Okay. People call these xk's Krauss operators, so you're acting by simultaneous left-right action on this tuple of Krauss operators. And then maybe I just want to say you that minimizing norms now for this group action, right now we can just start minimizing norms. Again, we do SL instead of GL, because for GL, minimize the norm, of course, would give you 0. We do it for SL. That's sort of the next best thing. And we can ask, okay, what is now the infinitesimal condition? What does it mean for the gradient to be 0? It means exactly that you transform your completely positive map phi by manipulating these Krauss operators like so into another completely positive map, possibly by taking limits, such that the resulting map is unital and trace preserving, which means exactly what you think it means. Unital means phi of identity is the identity operator. Trace preserving means, well, trace of phi is A is equal to trace of A for all A. Okay. So that's, people have called this the operator scaling problem. It's in some sense a natural generalization of matrix scaling for many reasons. And it's related to cool problems in theoretical computer science that you're very welcome to ask me later. It has nice interpretation in terms of non-commutative algebra and so on and so forth. But I think many of you have seen this already, so I don't want to maybe go through it step by step again for you. Okay, but very welcome to ask questions about that. Either interrupt me on the next slide or at the end of the talk. Okay, so it's like an extremely rich problem. And in some sense, it's the one that is non-commutative that we understand best, right? Where we have sort of the strongest results we can hope for. But there's also sort of lucky coincidences behind that problem that make it not as hard as the general problem I set up in this orbit problem slide, general norm minimization and so on and so forth. Okay. In some sense, there's some hidden total unimodularity in the problem that makes it sort of more tractable. Cool. So I want to talk about a more difficult setting where we don't yet have efficient algorithms and sort of incomplete understanding, but which is maybe more interesting to many of you, and also fits in the framework. Okay, so I want to apply the same philosophy that we saw for matrix scaling in detail and for operator scaling only very briefly to the tensor action of, again, I'm going to do SLN times SLN times SLN, so triples of invertible matrix determinant 1 on 3 tensors. Okay, so what's the idea? Okay, I want to define a normal form of T such that in the end, that will characterize the orbit, not only the orbit, but the orbit closure, the equivalence class of T up to local unitaries, up to the unitary action of UN, SUN by SUN by SUN. And the way I'm going to do it is I'm going to simply minimize, again, the L2 norm of over the orbit of that starting tensor. Okay, so G is an element of that group, so it's a triple of SLN matrices. I'm letting it act as before by G1, tensor G2, tensor G3, applied to T. And the infimum, that's okay, something that attains this infimum, sounds paradoxical, is going to be my normal form. What do I mean by that? Well, I'm really minimizing instead of infimizing over the orbit closure, and then the point S in the orbit closure, or a point S in the orbit closure, that achieves this minimum. Now this is right. This is a closed set. It's going to achieve its minimum when I minimize norms. Okay, is maybe called a normal form. Okay, so that's what I'm looking for, and I want to understand. Is there any interesting structure behind these minimizers? Maybe for matrix scaling, we saw it's exactly doubly stochastic matrices. I want to know, what does it mean for a tensor, a 3 tensor, to be sort of quantum triply stochastic, I guess, right? It's quantum because it's invariant matrices and not just diagonal matrices, and it's triply stochastic because I do 3 tensors, not 2 tensors. So what is the quantum triply stochastic? Okay, so let's talk about that. So I'll tell you what it is. So I want to ask, okay, when is S, such an S here in the orbit closure, when is it a minimizer? So when does it minimize this norm function? And again, the way one proceeds is one basically computes that in first order. One takes the derivative of the norm function in the neighborhood of the identity element of the symmetry group, right? And then the norm should better the derivative should be 0, right? Because otherwise you could decrease the norm by going in a certain direction. So if one does that game, okay, the answer looks as follows. And it's sadly a little bit more annoying to define than for matrix scaling, but I hope you bear with me. So what we do is the following. Suppose we have a 3 tensor S in the orbit closure of T. Okay. Now, when does S minimize the norm function? What do we do? Well, we first look at all the flattenings of S. Okay, so we think of S as a n by n squared matrix, and we singling out, each of the tensor factors. So K goes from 1 to 3. So we look at this flattening, and then we look at what you may call the Gra matrix or something. You look at Sk times Sk star. So Hermitian adjoint. Sk is an n by n squared matrix. The adjoint is an n squared by n matrix. So that's an n by n matrix, and by construction is positive semi-definite. Okay, so sigma k is sort of this Gram matrix-like object that you associate with the case flattening, and it's a PSD operator, positive semi-definite operator. So the quantum folks, of course, know that this thing is called the reduced density matrix, or the quantum state, or the quantum marginal of the kth particle, the kth subsystem. Okay, so sigma 1 is exactly the object, the mathematical object that describes to you the quantum state of the first subsystem, of the first tensor factor, the first particle, and so on and so forth. And so it's a quantum version of a row and a column sum, or I guess, I don't know, like horizontal slice, vertical slice, whatever slice, right? As you now might expect, setting the gradient to 0, so asking what's the infinitesimal condition for being a minimizer, is exactly saying, well, all of these 3 quantum marginals, all of these sort of quantum slice sums, should be proportional to an identity operator. Okay, it would be identity operator times the trace of any of these sigmas, if you want to be precise. Okay, or I guess you want to achieve this approximately, right, up to arbitrary precision. So people have called this the tensor scaling problem, an analogy to matrix scaling problem. Maybe it should be called the quantum tensor scaling problem. Okay, so it's given a tensor, find a scaling, so something in the group orbit of T, and that's as an engine, so that all these marginals, all these quantum row and column sums, or these quantum slice sums, are roughly uniform, roughly proportional to the identity matrix, or as close to the identity as you like. Okay. So this problem is encoding the infinitesimal condition. If you can solve that one, solving that problem is equivalent to minimizing. And so it's equivalent to finding a normal form with respect to that symmetry that we picked. So that's kind of almost the only thing that we picked. We like equivalence under SLN by SLN by SLN. And actually, I think that has been proposed by Van Strate and collaborators actually many years ago as sort of a normal form for multipartite quantum states. Okay, so in some sense, that's the original motivation, I think. Okay, but it has many other connections. I'll mention one in the following. Okay. So, but that's really what it boils down to, right? So what you want to find is it's really the quantum analog of this matrix scaling problem. Okay. So now I want to ask, okay, what can you do if I mean, there's sort of 2 choices, right? There's sort of 2 basic choices. Two basic possibilities. I mean, one is that this infimum is strictly positive. Then you will find a minimizer will be a tensor, 3 tensor S, a non-zero 3 tensor, where the marginals are as close as you want or equals if you take the limit to something proportional to the identity matrix. The other option is that this infimum is 0. So there's kind of the normal form is boring. The normal form is a 0 vector. Okay. And I want to ask, okay, is there still something you can learn in that case? Okay, from this from these general principles. So what do we do if this norm minimum or infimum is actually 0, right? I mean, if we did this for conjugation, for the conjugation action of matrices, it basically says my original matrix was nilpotent. So it's a bit like the nilpotent tensor case. Yeah, so nilpotent matrix, all the eigenvalues are 0, even though you could have had Jordan blocks, but you lose all these Jordan blocks, right? When you let the ones and the Jordan off diagonals go to 0. Right? So in the conjugation case, all nilpotent matrices collapse to a 0 vector. Similarly here, for generic tensors, this infimum will always be positive for non-generic ones, but ones that are of interest to the world, and I think to many of you, this infimum can be 0. Okay. So what can we do? And the key to answering, or a key to addressing, to approaching this question is by sort of taking this characterization seriously, right? So, and remembering this quantum interpretation, right? The quantum interpretation is, you have a quantum state, you want to transform it by the tensor action into another quantum state, where these marginal distributions, these marginal states, they're all uniform, okay? And kind of, well, if the norm minimum is 0, basically it's not possible to do that, okay? You cannot make all the marginals uniform, okay? So then you might ask, okay, what else can I make them to? Okay, so for example, I mean, you start with a tensor, so I mean, your row 1, row 2, row 3, they are something. Okay, so now how can I change them? That's a natural question to ask, right? Maybe I can't go all the way to the identity, to normalized identity, but I can go somewhere. And what is that somewhere I can go? So that's the next question, okay, and that I want to ask. You could ask, okay, given a tensor T, and I allow myself the scaling, so I allow myself to apply tensor products of invertible operators and take limits. What quantum marginals, what quantum slice sums can I get? So what triple sigma 1, sigma 2, sigma 3 can I get? So that's a natural question to ask. It's also extremely interesting from a quantum perspective, right? It tells you something about the compatibility of local quantum states. But that's maybe not the motivation right now for us, okay? One basic observation is that, you know, which marginals you can get will only depend on the eigenvalues of these marginals, okay? Because in our group SLN, there's the group SUN, and we can use SUN to change the eigenbasis arbitrarily of these positive semi-definite operators sigma I. Okay, so you can answer this question if you can already answer the question, the possibly simpler question. You know, what are the possible eigenvalues of these 3 n by n Hermitian matrices, or n by n positive semi-definite matrices? Okay, so I want to build a mathematical object that encodes all these possible collections of eigenvalues. Okay, so I guess I work this again here. The answer to that question only depends on the sorted eigenvalues. We can even sort them, right? Because we can change the order also by unitaries. So let's encode them into an object. Okay, let's call that object delta of t. And I was a bit sloppy the way I define it here. So delta of t consists of triples of real vectors. And the first n components, they correspond to the sorted eigenvalues of sigma 1, the next n components of sigma 2, the last n components of sigma 3. So that's a subset of R to the 3n. Okay. And I look at all of these, so all of these sort of eigenvalues for arbitrary scalings of S, even allowing myself limits. I call that asymptotic scaling. And maybe it's a terrible term because when you think asymptotics, you think of taking tensor powers of a tensor, but here I'm just taking limits with respect to my group. Okay. So there's nothing, there's no, not many copies. Okay. So that's an object, delta t, that I can define. Okay, I have this little bar here. So the bar means I divide by the sum of entries. So I make all of these things because they're already non-negative. They were P, right? See, the sigmas are PC matrices. If I divide by the sum of entries, these are probability distributions. Lambda 1, lambda 2, lambda 1 bar. That's lambda 1 divided by its sums, lambda 2 bar, lambda 2 divided by its sums, and so on and so forth. Okay. So that's a triple of probability distributions. Each has n outcomes, and the probabilities are sorted, say non-increasingly. Okay. The magic thing is that these things are convex polytopes. Okay, I mean, or maybe it's not so magical to you. I mean, to me, it's still very magical. It goes back. I mean, it's really a special case of old results by Mumford, Kivan, etc. We pointed that out for the tensor action some years ago with TS and friends. So here, it turns out you get a convex polytope in R to the, right? So that's a subset of R to 3n. It's going to be closed because we allow limits, asymptotic scalings, but it's very non-obviously convex polytope because, the set of scalings is not a convex set. I mean, it's not like a linear, I mean, eigenvalues are also not linear functions of nothing, right? So that's not clear, but it turns out to be that. There's a nice rep theory, invariant theoretic description that maybe I'm sure was discussed by Peter as well. So this is our polytope, okay? And we can now try to relate our previous discussion to that polytope. So what is this polytope really, right? So maybe I should first say, what is this origin, okay? So the origin that I picked is not the all 0 point, but it's the point that is, 1 over n, 1 over n, 1 over n, and so on. So it's exactly the point that corresponds to sigma, these normalized sigmas, so to the sigma being proportional to an identity matrix, right? Because if I divide sigma, if I normalize sigma, I get a normalized identity matrix, okay? And the identity matrix has, of course, spectrum 1 on 1 on 1, and also normalizing makes it 1 over n, 1 over n, 1 over n, and so on. Okay. So the origin in my picture, and the origin that I should have in mind, is the all ones vector. Okay. And it corresponds exactly to setting the gradient for this optimization problem to 0, because setting the gradient to 0 was making these marginals be proportional to the all ones vector. So if my polytope if the set delta, my polytope, contained the origin, it would mean that this normal form is non-zero. That means you can set the gradient to 0. So the minimum actually exists. Suppose this origin is not in the polytope, like it is here. Okay, so here it has a polytope corresponding to some tensor. It's this W tensor that E1, E2, E2 plus E2, E1, E2 plus E2, E2, E1 that many of you know. So that's the polytope of this entanglement polytope, this polytope delta T associated with a particular tensor. And from the very fact that the origin is not contained in it, we learn that actually the normal form must be 0. Okay, but because we have this polytope, there's still information, right? If you just ask, what's the normal form, we just learn 0. But we learn more. We learn, okay, there's a beautiful polytope, and we can, for example, look at what is the distance between that polytope and the origin. Okay, and there are nice interpretations to that distance. For example, it's sort of the speed at which you can send your tensor to 0 by using the group. But we know we can send the tensor to 0, right? Because the norm minimum is 0, norm infimum is 0, so it's in the null cone. Okay, but how fast can we get there? Sort of in the units of your group action. So that's related to this L2 distance, for example. But you can look at many other distance measures, okay? You can look at some kind of L1, L infinities, you can add weights, you can minimize the relative entropy distance if you want, okay? And if you do that, you get, beautiful sort of measures and notions of, sort of tensor ranks or bounds and tensor ranks that many people in the audience and others have studied over the recent years. So I guess this instability that people have discussed in the CAPSAT context, by Grohoff and friends, that can be interpreted geometrically as kind of a way of quantifying that distance. Quantum functionals, I guess you're all fans. They are obtained by maximizing entropy with weights over this object. So it's also in some sense a distance measure. Stable ranks of forms. They can also be interpreted, but I mean, of course, they can be defined more generally over finite fields. For me, everything was complex. Okay, same for this instability here. So it's kind of algebraically reformulated, but really in the complex case, it's exactly a way of quantifying this distance. Okay. So, okay, I think that was one of the messages that I thought was maybe interesting. So let's maybe look at that for a moment. I guess another thing that's interesting is, which I guess I like to emphasize is, in some sense, there are interesting combinatorial objects, polytopes, that are being defined simply by writing down a 3 tensor. And they're somehow it's very implicitly defined, right? It's like, which marginals can I get from scaling my tensor? And so it's not like, take the convex hull of the support or something nice, right? So it's very implicitly defined. And actually the tensor, right, it's an n by n by n tensor. So in a space of dimension n cube, this polytope can be very complicated. So generally it has exponentially many vertices and facets in n. Okay, so it's a very succinct encoding of a complicated combinatorial object, which maybe partly explains why it's hard, why it's difficult for us to find, super efficient algorithms in all settings. But it also sort of begs the question, right? Which interesting objects are sort of being secretly encoded here, right? So that was maybe a tensor example. So there's lots of other connections we discussed. We discussed these, this connection. That connection will come back in full force next talk. I mean, that's kind of where it started, null cone, orbit closure. These polytopes, I showed you examples of what are known as moment polytopes in symplectic geometry. Lots of things we didn't talk about. Well, optimal transport is related to matrix scaling. I don't want to go through the list, but it's more sort of to intrigue you into maybe looking more into this if you find that intriguing, that is. Maybe the last, I think maybe 10 minutes, I think we started a couple of minutes past. I want to talk about how do we algorithmically approach such questions, okay? What's the idea? And now I want to go back to the general setting. So a group action G and a vector space, okay? So really what we're interested in, right, for computing these normal forms, we want to minimize this function or infimize that function. For group G, we are minimizing the norm. And actually, I want to minimize the log norm because I want to treat the case that the norm minimum or infimum is 0. This null cone case, I want to treat differently, right, from the other one. The nilpotent case, I want to exclude. So I've put a log such that 0 becomes minus infinity, and the minimum infimum will just not exist in that case. So let's make things a little bit more concrete. Let's look at GLN, but you can also imagine any of the other actions you saw before by product of GLNs, for example. But GLN will still act in some non-trivial, interesting way on our vector. Okay, so same reasoning as before. Okay, if you have a norm that is invariant under, say, your unitary subgroup, which we'll assume is the case, then we can get rid of the unitary freedom. So really, we are by the polar decomposition minimizing over the positive definite matrices. Okay, so let's think of this problem, but minimize it over the PD matrices. okay, which we can write as e to the x for x Hermitian, similar as is in this chain of variables for matrix scaling. The positive dimension matrices, you can equip them with various geometries. You can think of them as a subset of the Hermitian matrices, where then that's a flat manifold. But you can also think about it as a Hadamard manifold, a sort of the non-positively curved space. And that's sort of the natural metric you get really by thinking of PDN as a quotient of GLN and UN. Okay. And there's an advantage to thinking about it in this way, which I'll tell you in a moment. Okay, now we have the setting, okay, and we can ask, what is the infinitesimal condition? What does the minimizer of that function look like? For that, what I should do is I should say, well, suppose I am at a minimizer, then the gradient would be 0. So I'm interested in the gradient at the identity as a function of my vector, okay? And that's just for the experts, that's what is the moment map in the background, okay, in the sense of spectral geometry. But a moment map is not so important. What's important is that I guess we saw in many examples that setting the gradient to 0 was actually the interesting problem. Okay, for example, in this matrix scaling problem, it seems like that's exactly saying, oh, I want a doubly stochastic thing and not something else. So it's actually not just a math trick, but it's very interpretable in many cases. Okay, and we call these scaling problems in the talk. So why do things work out? I mean, I already mentioned this before. So the point is that while this function restricted to the positive definite matrices is actually not a convex function if you think of the positive definite matrices as just a subset of the Hermitian matrices, and you take straight lines as the usual way. It's actually a convex function along the geodesics of PDN with respect to this negatively or non-positively curved metric. Okay, because there the geodesics, what they look like, geodesics through the identity, for example, they look like e to the xt, where x is a Hermitian matrix. Okay, whereas in the flat metric, right, it would be identity plus x times t. So that looks the same in first order, but of course not more generally. And it turns out that if you follow such curves, right, so that's a curve, I guess like in the picture here, through the identity with direction vector x. If you follow such curves, which are the geodesics for this curve geometry, then this objective function is convex. So the norm is log convex. Log norm is convex. Okay, that's really great results by Kempf-Ness. And so that's what made all, the things that we discussion from before, what makes it meaningful, right? Because it really says that critical points are going to be global minima. It's not quite good enough to have algorithms, right? For algorithms, you need a bit more structure. So you need something quantitative. I mean, usually, for a convex function, maybe you want that it's Lipschitz, or you want some other conditions. So that's the next thing, okay? We want to ask quantitative convexity. And here's something that's, it's not Lipschitzness of the function, but it's another, it's a very standard assumption, and convex optimization folks call it smoothness, okay? And smoothness basically means that, convexity meant second derivatives are d0. Smoothness means second derivatives are bounded from above, okay? Or the Hessian is, less or equal to a multiple of the identity operator, the multiple being the smoothness constant L, okay? So smooth doesn't mean C infinity, it means this estimate. And again, we take derivatives along these geodesics, these curved straight lines. So that's one thing. And somehow there's, for example, a general fact that if you minimize a convex function in Euclidean space and it's a smooth function, then you know how to analyze gradient descent in a good way. And similarly, that we show that that's also true on manifolds, okay, and particular on these manifolds that arise here, these Hadamard manifolds that arise here. Okay, this one looks a bit like a mouthful, so maybe that's going to be the last technical thing that I want to mention. But it is important, okay? So the point is, we have a primal problem, which is minimizing norm, and we have sort of a dual problem, which is setting the gradient to 0. And if you allow yourself to take limits, infimize norm, let gradient go to 0, that's equivalent. But of course, we want to do these things algorithmically and effectively, so we need a quantitative version of that. So I want to know, if I'm close to the minimum, is my gradient small? If my gradient is small, am I close to the minimum? Okay. So let's look at now at this sort of mouthful of a chain of inequalities. So let's first define f star to be the value, the infimum value, okay? And we assume it's finite, so we are not in this null cone case, okay? So then, okay, what is f star minus f? That's sort of the gap in the function value. So right, if you're currently at a certain point, you have some function value f of p, and f star is the actual infimum. So f star minus f quantifies how close you are to minimizing the function. So e to the f star minus f is going to be close to 1 if your function value is close to the infimum. On the other hand, the left and the right hand side, they're close to 1 if the gradient is small, okay, up to these constants that are floating around here. So what this is saying in a quantitative way that norm minimization and making gradient small, that is what we call scaling, are quantitatively related in both ways, okay. It also means that we can decide, is the normal form 0 or is it non-zero? because if the normal form is 0, f star is minus infinity. So e to the f star minus f will be 0. But if the gradient is smaller than gamma, the left-hand side will be strictly positive. So we cannot be in this unstable case. Okay. So it also implies, therefore, that we can solve what they call the null-com problem. It was the problem given a vector, and on my representation, is it equivalent to the 0 vector, or is it not? Okay. These parameters L and gamma, they depend on some representation theoretic data, which is in essence combinatorial. You can ask me about it. Not so relevant. So L is typically a tame, not too large number. Gamma is a number that can be quite small. Okay, and then we are in trouble because then we have to make this gradient similarly small. For example, gamma is only polynomial, inverse polynomial small for matrix and operator scaling, but for in the tensor setting that we're very interested in, it can be exponentially small. Okay, and so that's why we're working hard to find better methods. All right, so here's the summary then, and I think after that summary, I want to say one word about gradient descent, and then I want to close. So just summarizing what we discussed, okay, here's the general framework. We have some complex reductive group acting on a finite vector space. We are interested in, for example, well, is the normal form of V the same as for the 0 vector? Can V be distinguished from 0 vector or not? So if the answer is yes, it cannot be. We approach this by the idea of minimizing norms over orbits, orbit closures to be more precisely. Also saw that this gives good candidates for canonical forms that then allow you checking equivalence, okay, because it reduces the freedom from the group G to a compact subgroup. And then we can approach this, well, theoretically, because of geodesic convexity, in practice, because of these duality estimates I showed you in the previous slide, we can instead try to set the gradient to 0, or more quantitatively make the gradient small to solve that problem, okay. And all these examples, and also the ones we didn't really discuss on the bullet point list, they fall into that framework. Okay, this convexity explains why simple algorithms have a chance of working. Simple algorithms such as local algorithms like gradient descent, Sinkhorn's algorithm, quantum versus Sinkhorn's algorithm. That probably you have a natural guess that that one exactly works. And yeah, it makes it quantitative. It can be thought of a bit of a non-commutative generalization of geometric programming, if you like. And then, of course, to make it effective, we do provide algorithmic solutions, which work fantastically sometimes and not so well in other cases. I don't know, let me just look at the times, 2 past, so I think I should close in a couple minutes. Jon, can I say one thing about gradient descent? I'm not sure exactly when we started.
Yeah, you can say
the boss. Okay. All right. Then, okay, I'll just want to give you just one theorem. So that you get a flavor of what one can prove, okay, after all the stories. I mean, I'll show you a very simple looking theorem. And the idea is really, okay, we want to now solve this problem. I mean, we know that everything in the end boils down to minimizing norms or setting gradients to 0. We have something that is convex on a curved space, but still convex, okay? So the first guess is let's do gradient descent. And so that's one of the algorithms. And what does gradient descent mean here? Well, you compute the gradient. It's going to be for GLN, it's going to be Hermitian, or for PDN, it's going to be Hermitian matrix, e to the minus 1 L. This will be a group element, and you simply apply a little gradient step, right? Gradient step is you exponentiate your gradient with a small step size. So like this guy's roughly identity minus 1 over L times the gradient, right? So like slightly moving in that direction, but using in the group or in the PD matrices. Okay. And then, for example, you can show, and most of that is standard, but there's one piece that is not. The following: if the gradient can be set to 0, okay, so if you're not in the null cone, if the normal form is not the 0 vector, then this algorithm will output a group element. So, well, if you do that with the right choice of L, namely the smoothness comes from before, such that the gradient is epsilon small, and it will do so within a time that's polynomial in 1 over the precision that you want, how small you want the gradient to be. And okay, that's the easy part, but it's also polynomial in the rest, in the input size, and that's for any algebra action of, say, a product of G lens and S lens. It's not just for like a simple representation. Okay, and so the way one analyzes such things, okay, there's like a standard thing which kind of shows that because of the smoothness, you can sort of trust your Taylor expansion to second order to some extent, and then you actually do decrease the function in each step. Okay, you can control the Taylor expansion because between 0 and L by L smoothness and convexity. What's not so hard, I mean, usually that's great, but then sort of to really make progress is that kind of you have to know how small can F be without running the program, right? Because I mean, each step you decrease F, you know where you started, right? You start with a norm of whatever you started. That's going to be polynomial log of the norm that we started. So f will be polynomially large in input size. But then maybe you can make the norm super tiny, and then you have to go a long time. Okay, and so one needs a priori bounds. Okay, and it's what's fun is that these are actually constructed by using tools from invariant theory. Okay, so algebraic tools. So we kind of prove bounds on, say, the complexity of the coefficients and degrees. Well, not degrees, that's what harmed it, but on the coefficient size of invariant polynomials that you need. Okay, and so we use invariant T, but to analyze numerical algorithm, which is kind of, I don't know, I find always very amusing. Okay, all right, and then if you apply that as before, if you pick epsilon small enough, less than this constant gamma from the duality, as I explained, you can solve the null conform exactly. So you solve exactly this algebraic problem. Is my thing equivalent to 0 or not? For David, in a moment, it will mean, does my tensor network, does my tensor generate a non-zero quantum state for any system size or not? Okay, in the time that's indicated here. Okay, so that will be polynomial time if gamma is, say, inverse polynomial small. All right, so you can do Newton steps as well instead of gradient steps, but we won't. So I'll just want to wrap up. So thanks a lot for bearing with me. I hope it was enjoyable despite the transatlantic lag and the challenges of Zoom talks. So I want to explain, I guess, motivate from the fact how can we figure out when two algebraic objects are the same. So encoded by equivalence under group actions and taking limits. That captures interesting problems. I guess hopefully you saw some problems that you find interesting, and if not, that maybe in this list some things intrigued you. Interestingly, there's polytopes at play. These polytopes can give more information even when naively the normal form is not informative. Okay, and we saw that that's really interesting for tensors. It reduces many clever notions that were introduced. They kind of can be seen as sort of a shadow of these polytopes. And then to make build algorithms around that, for example, to compute such quantities, right? The idea is to rely on ideas for optimization, and we can do that because secretly these objective functions satisfy a kind of convexity. Okay, and right, so there's lots of things we don't know, but probably you have other questions we want to ask. So thanks a lot for your attention.
Any questions? Yes.
Hi, Michael. I have a question. Your dependence on epsilon in your last theorem, is that optimal, or could you expect that it depends on log 1 over epsilon?
Yeah, it's a great question. So the part I skipped will actually. I gave this first order method, right? So gradient descent in general, if you only know smoothness, you wouldn't expect you can do better. In some settings, you can prove that you actually have strong convexity. So your Hessian is not only large equal to 0, but larger than a constant. And then it's a bit like the conditional of the Hessian is bounded. Then or even gradient descent does better. And that happens in some applications. So for example, if you pick a random tensor and you try to minimize the norm, okay.
Yes.
And there's some nice statistics applications for that where random tensors correspond to random samples from a Gaussian and so on and so forth. So that's one answer. So sometimes that does better. And actually then it's really generally polynomial time, right? And all the parameters with high probability. The other answers in general, you can do smarter optimization methods. You can do Newton steps, for example. So second order methods instead of first order methods, where you basically trust a little your Taylor expansion to second order. And then what you get, and that's kind of somewhat ironic, is you do get a log 1 of epsilon dependence. So that's really like, proper polynomial time, you would say. But there's a pesky dependence still on this constant gamma that I had before. So gamma was this, one constant in my duality theorem, in my quantitative duality relation. So the thing that relates how smallness of gradients and how close you're to the minimum in one of the directions. And that enters our bound here. And I mean, we know that this gamma can be bad. Say for in general, right, if you know nothing about your tensors, for the tensor action, or even for nice tensors that are free, one can construct counterexamples. So I think somehow there's two ways of interpreting it. I mean, I guess the way I interpret it is as follows. If you restricted these algorithms that we are formulating here to commutative group actions, right? Then I explained this all reduces to geometric programming. And we know how to do geometric programming in polynomial time, but not in using these algorithms. Okay, so this is like not a polytime algorithm for geometric programming in general. It's a more naive algorithm, sort of, before the revolution of the 80s. And so what we are sort of thinking about, sorry, it's a very long answer. What we're thinking about is indeed, can one generalize these more sophisticated tools like interior point methods, ellipsoid method, to manifolds to get a sort of a proper polytime algorithm? Or is it the case that really this curvature bites you in a way that you cannot overcome algorithmically? So, I mean, I'm optimistic, but but it's really an open research question.
Okay, thanks a lot. So it was a very encompassing answer. Any more questions? No? And then we will head for lunch. We'll say goodbye to our online participants. And before we're properly heading for lunch, I wanted to say thanks. I will unfortunately leave you already after lunch, so like at 2 o'clock. And I just want to say thanks to Jeroen a million times for these 2 weeks. It was really a great workshop and for carrying all of this through. Also want to thanks to the CRM and our technical assistant over here. And as you saw, I also want to thank our remote participants, which are now on the screen again, and for giving all their talks, and for missing out on all the coffee breaks and lunch breaks and all the fun dinners. Right. What else I want to say? I want to say you have a room for tomorrow.
Yeah.
I think you should have received this. So it was worth flying over. So you don't have to sit in your hotel room and watch the show from there. Yeah, so thanks, Jeroen. I also want to thank one more person, that is Luc René, who was the director of the CRM and who I've known for many years. And Luc has somehow set this whole thing in motion. He has orchestrated for when he's orchestrated a 3-month program. And this is kind of like 1 month of the 3 months, but then sort of not, I would say, unexpected. Luc took some, how do you say, again, like some bigger administrative positions. So he is director of IVADO. It's basically Quebec's AI initiative. So he couldn't be here, but I think we had a very good time, and I wish you all, happy afternoon and happy tomorrow, and then happy flight back. And it's great that Alessandra stays here, for a longer time in your room. And I guess if someone wants to stay longer and hang out with them next week, I think that should also still be possible. Okay, well, thanks from my side, and